Hey, welcome to another coding session. Cracking along with Bangalang. In the last session, we created a few primitives for multi-threading. We created some atomic integers, which are kind of like building blocks. Building blocks, it's like a small thing we needed that ensures that if we do a plus equals or a minus equals, that's not going to get interrupted by some other thread. Then we also made semaphores, which is basically just a specific usage of an atomic I32. When we signal, we increment the semaphore, and when we wait, let's have a look. When we wait, we decrement the semaphore, and then we check, like, after we decremented it, is it still above or equal to 0? And if it was, then we say, okay, the decrement was successful and we continue. Otherwise, we undo our decrement. So basically the idea is that when we're waiting, we're basically waiting for the semaphore to become positive. When we declared it here, it was a 0. So then when we say, let's wait, we're saying wait for it to become positive. And our signal here is incrementing it by 1, which is going to make it positive. It's going to change it to 1. So that's the idea. So you could signal it 5 times, and then 5 waits would be able to continue. Yeah, that's the idea. And then we have a mutex, which is like used for locking. So if we have some resource that we want to access from multiple threads, before we access it or modify it, we can do a lock, and that'll ensure that any other thread that comes along and tries to also lock, they will be blocked until the first lock is unlocked. So you need to lock, and then you need to unlock before you can lock again. Yeah, so that ensures that only one thread at a time is using a certain resource. That's the idea. I'm just going to cut all this stuff out for now. I know we should probably put it in our test suite, which I said at the time when we made it. I was like, now when we make new features, we're going to have tests. And I totally didn't do that. It's on my to-do. I think I really wanted to get like this multi-threading going because I've been talking about it so long. And then once we have multi-threading, something interesting with multi-threading, then I think the next thing after that is like we really need to beef up our testing, because at the moment it's just really not good. Okay, so today we're going to make a thread pool. Yeah, I'm just going to do like piece by piece, because I'm pretty sure we're going to come across some bugs and just some things that we haven't implemented yet, some features that we need. So to start with, I'm going to define a struct, which represents a task that we can put into the thread pool, or that we can have the thread pool execute. So it's going to have a function, which is a procedure that takes, I'm going to just, for now, I'm just going to say a slice of floats. So then we also need to supply that slice. So if we create a task that is a function to execute and the data to execute in that function, then later down the line, we can do something like task.data to then execute that function with that data. That's the idea. Okay. And then we want to create a thread pool, another struct. We're going to need a work account. I guess I'll make that an I32. So that's how many workers are in the thread pool, which is kind of to say like how many threads are we going to allocate to the thread pool. And we're going to have a list of tasks, of course. Just to keep things super simple, what I'm going to do is I'm going to say this is a thread pool task array just with 100 in it. And then I'm going to have a task count, which I'm going to make an I64 for silly technical reasons, limitations in our language right now. If you're going to index into an array, you have to do it with an I64, and I want to index into it using this variable, so that's why it's an I64. Yeah, I think that, oh, and we're going to need some synchronization, some primitives. That's why we made them in the previous session. Okay, so, and actually this stuff I want to put in the standard library. So let's put it here. Okay, so we have a task and a thread pool. Next thing is I want to be able to add the task to the pool. So thread pool in Q is a procedure that takes a thread pool and a thread pool task, and they're both pointers. And that procedure, how is that going to work? Well, we want to modify these two parts of the pool. Now, potentially, we could be in-queuing from multiple threads. So what we want to do is first do that lock. Mutex lock. So that would be, we need a pointer to pool dot mutex. Now we're going to lock. So basically we're locking the pool so that we can then modify parts of the pool, and we won't get interference from other threads. Now we're already coming across an issue because I'm just doing pool.mutex, but pool is a pointer. So we need to auto dereference pool so that we can access a member of it as if it's just a value. So we need to add auto dereferencing, which is in type checking. We already have auto dereferencing when we index into an array. If we have a pointer to an array, then when we index into it, we auto dereference it. So we convert it to the value that it's pointing to, and then we perform the index. And that's one of the implicit things in the language. And this code here is basically doing that. It's saying, you know, if the thing we're indexing into is a reference, then we wrap it with a dereference node so that it gets dereferenced. So I'm going to say auto dereference the child node. So I'm just going to extract that out to its own procedure. Auto dereference proc. I get a bit confused sometimes because the Odin syntax and the syntax of my language are quite similar, but they're not the same. So sometimes I get confused between the two. Okay, so we don't need to say the child anymore. We're doing it on the node we pass in. That makes sense. So I'll just call this a type node. Another thing I like in my code is to do, they're called like guard clauses or early outs. So instead of having all of this wrapped in an if, I just invert the condition and return out early, you know? Because we're auto dereferencing, which only makes sense if we're talking about a reference. If it's not a reference, then there's no need to dereference. And anywhere where we have .child0, we need to basically strip it off. Like so. I mean, this one's different, that's part of the type node, keep that. Because where previously we were yeah, we were in here. So we were always referencing the first child directly. Now we pass in the first child. So it's just the node. But since it's a pointer, we need to dereference wherever we use it. And do we still need to dereference this? I think so. Because the thing is that we're getting, this get type is getting a pointer to one of the children of node, but then we clobber node. We replace it with this. So the pointer returned by this would be invalidated, which is why we dereference it. So effectively, this is a copy of the type, which we need because we use the type down here after we've done this. Okay, so, oh yeah, up here, I think we need to go like this, maybe. Is that happy? Oh, now we need to dereference here. So all I did so far was just dereference, auto dereference. Oh, or I just like extracted that code, and the reason is because now when we come down to identifier, if we're talking about a struct member, we also want to auto dereference. Here we can just use child node. And hopefully that works. Okay. Line 52, oh, that's because we don't have a comma here. I don't like this. Really, it should be complaining. It should be saying, I'm not sure exactly what it should be saying, but something more to do with the error in here, instead of just saying, hey, somewhere in this struct there's an error. I'm not sure why it's doing this. It's not very nice error handling. I need to figure it out at some point. But I think it was just because I was missing that comma. I think that's what was wrong. Okay, exit code 0. Probably because we don't actually do anything. So let's create a thread pool with a worker count of 1. That's just going to be easy for testing to start with. And also our threading, the way we do threading is not great. We can't actually handle spawning more than one thread. We'll get into that later. But for now, we'll just say there's one thread in the thread pool. And now we'll create a task. So thread pool task. And we need to set the func. I would like to be able to just go like this. You know, just assign, so that would become the body of the function. But this is effectively making like an anonymous function, which we don't have support for. So I just need to define it up here. So I need to get the right signature, like that, and go like that. Now, I think actually this is already also going to be trouble, this line here. Firstly, I don't think we've ever assigned a function as a member of a struct. And secondly, from some playing around I've done, I think even if it was like this, I mean, let's just do this to start with. I think this is broken. It was working at some point, but now I think it's broken. So let's see what happens. So we should get we should get 3 assignments in our main body of our thing, but we only get 2, right? So this one is creating our thread pool, which is huge because it has 100 of these in it. And the second assignment is just assigning 1. See that there? But the third assignment does not exist. There's nothing here. I think we'll find that it actually has created a func function. Here it is. It's a func function that does nothing. So really what we want is for that to be Well, maybe this is actually a difficult situation. There's some ambiguity here, which I'm a bit afraid of and I don't want to deal with. And so when we do it with a member, a struct member, there's less ambiguity actually. So let's actually do that. And if we go to the top, there should be 4 statements now, but there's only 3. So this third one is creating the task. That's this here. And this doesn't exist. So let's try and fix this up. Now the way I want to do this is I want to introduce the concept of allocators in a very simplistic way. So everything so far we've allocated on the stack. And we have also been, I guess you could say that our procedures are allocated statically, which means that they're embedded directly into the executable. You know, they're down here like this. Here's a procedure. And there's also variables that are statically allocated, strings and things. So when I say statically allocated, it kind of means like just embedded into the executable. When the executable starts, they already have their values. You know, like when our code starts, those values already exist. So I just want to kind of explicitly say with procedures that in some cases they are static and in some cases they are stack-based. See, this is static, this is stack-based. So when we do this assignment, it should take the address of this and store it in this stack variable. That's the idea. So if we go to our AST, I think this maybe should also be a node, but I'm lazy. So we're just going to add an allocator string here. And then I think also in type checking, when we type check our assignment here, this is where we're sort of creating our procedure. Or, yeah, this condition here is like if the left-hand side has the type procedure, which is the case like here. This is an assignment where the left-hand side has a procedure type. Then we're saying do the special stuff, you know, type check a procedure body and everything. But in this case, this also has the type, a procedure type, but we don't want to treat this like a procedure body. We just want to do an assignment of this to this. So I'm going to say allocator equals static. So whenever we declare a procedure body, we say it's static. But we don't want to go in here if it's a member. Okay. We don't want to do that. And that reminds me actually that because of this other code that I've changed here, when I auto dereference, not in the index, but in the identifier here, we've figured out, okay, it's a struct member. We auto dereference. But now the problem is, yeah, now well, if we auto dereference the type of the child node, no, the type of the child node should be correct. That should be a struct. Because when we dereference, the type becomes the thing that was previously referenced. Okay, sorry, I thought there was like some trouble here, but I think it's okay actually. But I think this is struct member does have trouble. Yeah, because this here, so if we have a look in the tree, this here is how it looks like in the AST when we have a struct, you know, we have like foo.bar.baz, so we have a struct and then a member of that struct, which is also a struct, and then a member of that struct, which I guess is a pointer to an array. So we want to dereference the array or the pointer and then index into the array. It's a bit complicated. But see how we have like the stack of identifiers when there's members of structs? That's what this is trying to point out. But the thing that we're getting at now is that this here could be a pointer, which we want to auto dereference when we access, like if bar is a pointer to a struct, we want to be able to say .baz to get baz, which means that in between these two, we would need to have a dereference node. So this is struct member where we check, like, is the current thing an identifier node, and does it have a child which is also identifier node? That doesn't work anymore because the child might be a dereference node. I hope this kind of makes sense. I feel like the problem with this series is that it's getting to be very abstract, you know, and probably kind of hard to understand, but I hope you guys can kind of follow. So what I'm actually going to do now is invert this condition equals, and then say that means that it's not a struct member. But like I say, this is not really valid. So instead, what I'm going to say is, if it's a type, then we quit out. Then we say that's, like, if the first child is a type, that basically means that we're not talking about a struct, because otherwise the first child would be basically representing the struct that it is a member of, instead of it being a type. So this should be a pointer to the first child. And then we're going to do something like this. So now we're saying the first child is representing, you know, the struct. So we want to get the type of it, which could be a pointer to a struct. And we want to check, and basically we want to check, are we talking about a struct here? Is this type a struct? So that's why we want to do get type value and say, is that equal to struct? Actually, I don't think I did the square brackets thing yet for struct. I did it for some other special types, but not for this. So this is the keyword struct, so that doesn't change. That's also the keyword. That is the type. This is talking about keyword. This is the type, and that's talking about keyword. Okay. Now there is still even another little flaw in this. Because when we get the type of the struct, it might be a pointer, it might be a reference node whose child is a struct node, and that's what we want to identify. But then the struct node is also going to have children which represent the members of the struct. And get type value at the moment, the way it works is it drills right down to the bottom of the tree for the type. And we don't want to do that anymore. I think as long as we drill down until we find some value, that should be good enough. Well, that should be actually more correct. So now it'll drill down, and once it finds a value, it'll return it. Yeah, only if there's no value, then we recurse further down to the tree. Otherwise, we don't. And that should mean, where were we? I don't know anymore. Yeah, that should mean that we get the struct back. So all of this to make sure that is struct member works, which is now going to create a different problem because now this wants to get the type of the child. But if we have not type checked the child yet, then the child won't have a type. So we need to bring this up here and say something along the lines of, if we have a child which is not a, and the first child is not a type, then we can type check the primary. Like so. Oh, so if we have a child, that means that's greater than 0. Okay. I think that should hopefully work. We get exit code 0, which is a nice start. We still don't get our assignment, and I think that's because I think we have added static. Yeah, we kind of got sidetracked a little bit there because this was to do with this is struct member, making sure that's correct. But so we've added static to our procedures, and now we want to do some stuff based on whether it was static or not. In generation, basically we want to say, like, here, this is where we decide whether we're going to make a statement or further down we're going to make a procedure. So I think we need to do an extra check in here. It needs to be a procedure, and it needs to be a static procedure. Right? And in this case, if it's a static procedure, then we don't generate a statement. And if it's a static procedure, we do generate a procedure. Okay, we're getting an error. So let's see what the error is. It's trying to copy to an immediate. Why would it be doing that? It's an assignment, so the destination is immediate func. So it's trying to copy to func. I think I might know why this is. Where are we? Yeah, this is in generating a primary, and if we go down to here for an identifier such as func, it's going to see that func is a procedure and say, okay, this is the location of it. But like I was saying before, this, because it's not static, this should be stack based. So basically what we should be saying here is if we're dealing with something static, then we return it as immediate. Because it's embedded directly in the executable, we can refer to it by name. Otherwise, we do all this normal stuff that we would do to get the stack location of it. Something I'm just noticing here also is this. Because this is where we're trying to figure out, yeah, whether it's like a member of a struct. And I think, again, kind of like in that is struct member, this was not enough anymore. I think that's also the case here. I think we need to do with node. Yeah. Okay, so hopefully that will fix that. Exit code 0. Okay. And now we have 4 assignments. We got this now. So task func is getting copied to the top of the stack. And the top of the stack is this newly created thing. This. So if func is the first member of this, then that should be correct. And it is the first member. Okay. All right. Cool, so we've gotten this far, not very far yet, but let's actually call thread pool and queue. We did a bunch of changes to hopefully allow that the first line in thread pool and queue. So let's see if that works. Well, we got exit code 0 at least. That's a nice start. And if we go thread pool and queue, it looks kind of right to me, I think. So we're allocating 8. We are dereferencing because we need to dereference the pool. So that's what we do. We get it in here, and then we offset into the thread pool and reference that. So we need to offset into the pool to get mutex, and then we're referencing it. So that makes sense. And then we copy that onto the top of the stack, which we just allocated as, so that's the parameter to mutex lock, and we call mutex lock. And we deallocate. I think it looks good. So now the reason that we did the lock is because we want to actually add to the task. So pool.tasks, pool.task count becomes the task. And then we increment this. And now that we're done, we can unlock. So we locked so that we could do this and make sure nothing else interfered while we do that. So let's just see if that works. Looks like it does not. So let's just check. We know this line works. So this line, it looks like does not work. Let me just check. Is that, okay, so it's inside the compiler that something's going wrong, which is good, because if it's something in the assembly, it's a pain in the ass to debug. So we don't have a type. Tasks does not have a type. Okay. Index node and tasks is a child of the index node, and it does not have a type. The index node has has 3 children, so I guess it does have a type. So why does that not have a type? Was it not given a type? Where should it be? So this should all, during parsing, get created. When we're parsing like kind of here, I guess. This is, if we have a period, so we're accessing a member now. Okay. Remember, index has 3 children. I don't know why we're saying it has to have 1 for it to be considered not a leaf node. That seems silly, actually, to restrict it to only 1. Like, if it has children, it's not a leaf node, so keep going until you find it. That could possibly be it. Yeah, well, now we have xcode 0, which is nice. Oh. Probably should have stayed there. Thread pool and queue. Okay, that's got all this. It's a lot of assembly because it has all this bounce checking and stuff, so let's just assume that it's right for now. This one should be fine, right? Yeah. And then we unlock. Okay. Now we want a signal. So we want to tell the pool that there's something ready to process. Basically, that's what the signal is saying. Like we've added a task, so now we say, hey, pool, here's something for you to do. And that has a segmentation fault, of course. So that's here. So we allocate for our parameter. This is basically what we did before, like up here for lock and unlock. So we dereference the pool, then we access the member of the pool, copy it into our parameter for semaphore signal, and call semaphore signal, which then basically just increments the semaphore. So we dereference the semaphore, which is RSP plus 8. Yeah, that's where the parameter should be. Put 1 into R12D, and so that we add 1 to it. And then we copy that. It's a return. But back here, we only allocated 8. If we call a procedure and we want to return as well, we need to allocate space for that return, but we haven't done that. I think the returns in my language need a lot of work. They're pretty messed up. Because this is just an expression and it has a result, what happens is this gets wrapped in a return node and it returns, but see, this procedure type does not have a return, which is why we don't allocate for the return. Probably just like a simple little fix could be to do this. By wrapping it in a scope, that means that this will not become a return statement. Yeah. So now semaphore signal should be, so it doesn't have that copy anymore. It's just an increment. Okay. We should do something about that. We need to handle our returns much better. I think also the type checking of returns is basically non-existent. You could just like return whatever the hell you want. Also, you can't have a return that doesn't return anything. Like if you have a procedure that doesn't have a return type and you just want to return early, it's not possible in my language right now. Which is why we have things like I showed you this procedure earlier. See, we return true. Ideally, I would just like to have it like this. It doesn't need to return a bool. I just need it to return. But because of limitations of my language, we have to return something. Okay, so I think we have something enqueued now. Before we get into too much more, let's see if we can just call it before we get into like multi-threading. I have a feeling this is not going to work. Yeah, undeclared identifier func. So yeah, we don't do this very well. So let's go to our call. Where's call? Type check call. See, it's expecting the name to be in the list of identifiers, so expecting it to be a variable. But here it's a struct member. Here it's a struct member, so it shouldn't be a variable. And I did have a bit of a think about this because I knew this was going to come up. I think we need to adjust our grammar a little bit. At the moment, a call is an identifier followed by brackets with expressions in it. Hey, why is this right-hand side within the type primary? That should be type primary. So what I'm going to do with this call is I'm going to take the identifier off, and over here in the right-hand side primary, where we have call, instead of it being like its own independent thing, I'm now going to make it, I'm going to put it here. So let's go back to where it's formatted nicely so you can see what I did. So call now is just brackets with expressions in it. And in the right-hand side primary, where we have one of the options for a right-hand side primary is it can recurse. It can be a right-hand side primary followed by one of these things, of which call is now one of them. And that should allow us to be a bit more flexible. So hopefully by just making these changes, it will become clear why. So parse call now does not have this. That's not part of a call, the name node. It's just brackets with expressions. And this is not where we do the parse call anymore. I'm just going to steal this. If we come across an identifier, we just parse an identifier. This is parse primary. And instead, down the bottom here, so these are the things that can appear after a primary. We're going to add opening bracket. And this is only for a right-hand side primary that this is allowed. I'm going to do something similar to what we do here. We're going to say store our node as the child, then do the parse call, and then add our node as a child. But the thing about this is parse call is going to add a bunch of children, which are the parameters. And previously we had the name node at the start. And I kind of want to replicate that sort of structure. So instead of, this will add that name node at the end. So instead I'm going to go inject at index 0 so that it becomes the first child. So it should be still the same kind of structure, a similar structure. But now in type checking, when we type check a call, where are we? Type check call. This is not part of it anymore because the call is just the brackets. It's not, the name is not part of it anymore. And instead, it is the identifier is the child. So actually, we want to do like this here. But what I think I'm actually going to do is take this out, because I think basically all of these cases have something like this, right? See, type check primary, type check primary, type check primary, type check primary. So now I'm just going to put it up here and say like, look, if there is a child to type check, let's do it. And then we don't have to have it in all these cases. And then when we come into here, that should mean that this first child is already type checked. I'm going to call it the identifier node. And basically that's that node. Maybe that could just be a type node. Yeah, like that. I think that's fine. Is it still necessary to do this? I don't know, we'll just leave it for now. This is taking the type of the procedure and propagating it up to the call node, up to the this node. It's taking it from this node and moving it up to that node, but just changing the name to call. Yeah, let's leave it. I think it will probably get into trouble if we try to change that. So I think that's the type checking adjusted. And we shouldn't get this error anymore. But we also need to change the generation since we've changed the structure a bit. So now we're generating a call. So we also need to generate the call of the child first. And I think I want to do something similar to what I just did. What I just did here, you know, where we recurse first. So this is generating the primary. And now I want to put generate primary in here. a location, I guess it's the child location, because we're getting the child node, and generating it, which should result in a location, which means that we don't need this here and here and here and here. Anywhere else that we have it here. Okay. And while we're at it, I kind of already rename these. I don't like that naming convention. It's just the location. Okay, I think that's it. So we need to rename these to child location, like so, and down here, here I think I'll go location equals child location, and then we just want to offset it before we return. We're taking the child location, so this is where it's a struct member, right? So this is a location of the struct, and this is offsetting into the struct to the member that we want. So kind of conceptually, it's like a different location. That's how I think of it. Okay, I think that's about it. So what happens when we run that now? Symbol func not defined, which is true. Func should not be defined, but we should also not be trying to call func here. And I think that's because when we generate our call, which is here it is, we're just taking the name of the procedure and we're saying call that name. But that's not going to fly anymore, because sometimes when we get to generate call, the child location will be the location of the identifier, right? So for a static procedure, it will still be the name, but for a non-static procedure, it's going to be a stack address. So I think what we need to do is actually pass that in here and use that as the thing that we call. Like so. So let's change this also. We called that identifier node in the other place. So let's be consistent. And then when we come down to here, since it's going to be a stack address sometimes, I'm actually going to keep this here so that we can give us a bit of a hint as to what it is. But we'll put the child location in here as an operand, so that will go there. So that will either be the name of the procedure if it's static, or the stack address if it's not. And that kind of handles this case as well, because this was trying to do stack addresses. So I think that should do it. Okay, segmentation fault. But at least now we're trying to call R11, which is the value at the top of the stack. Which was this here. Yeah, so I think that's right. I think that's right, but we have issues. Is it in the compiler we have issues? No, it's in the execution we have issues. So let's just double check that it is, in fact, this line that's causing the issue. No, it's not. Okay. So what if we comment out this? Okay. So somewhere in thread pool and queue, we're getting an issue. Let's try this. Okay. So now this is causing an issue, right? If I comment that out. Okay, so we did something that broke this. So if we go to thread pool and queue in our assembly, what do we see? It looks basically like what we saw before. It looks good. I don't see immediately an issue there. We're calling mutex lock, which is defined up here. So maybe I'll go to mutex lock. So if I just give that an empty body, let's not do that because it does confusing things to the comments here. Okay, so it has an empty body, then it's happy. It's calling compare exchange. Okay, yeah, I think this could be because we added this static thing that we should have put, because these procedures are also, I mean, syscall isn't really, but these hard-coded procedures are also static. So we should, oh, that's value allocator. So we should also put allocator static on these. So you compare exchange. Because it wasn't static, oh yeah, I was doing that. But see, like it's calling compare exchange by providing an address, which is wrong. I don't even know where it gets that address from. There we go. Exit code 0. Yeah, and see now it's calling it with the name. Yeah. So that was the issue there. Hopefully I can uncomment this and everything is happy. And then hopefully I can uncomment this and we should get it printing out task. Good. Okay, great. So we have something in the thread pool. We're able to execute it. So we need to start the thread pool, because the thread pool at the moment is not actually running any threads. So I don't think we need brackets actually, but to start the thread pool, basically we want to loop through for the amount of workers. While that's less than index. I know I can do plus equals 1. Unfortunately, it's a quirk of our language at the moment. One of the many quirks, that in a for loop, it has to be an assignment here after the expression. So this has to be an assignment, and index plus equals 1 is not an assignment, it's a right-hand side expression. So it doesn't pass parsing if I do that. Okay, so we want a thread start, or I think it's called start thread, with, I'm going to call it a thread pool worker, and pass in the pool, a pointer to the pool. Because the way start thread works is it needs to be a procedure that takes in an I64. And that's why we need to sort of take away the type checking of pool. But pool is a 64-bit value, so it works. Pointer is a 64-bit value. And then in here, we need to convert it back because we want to treat it as a thread pool, like that. So this will start a new thread that calls this procedure. The way we pass things is just by I64 right now, and then we get back our pool pointer. And the pool, or the worker, is just going to keep looping, and in every loop, it's going to wait for a signal from the pool, right? So basically it's going to wait for this to happen. It's going to wait for something to get added to the pool. And once something does, it's going to lock. And when it's locked, the first thing it's going to do is decrement the counter, which means that this is going to be pointing to the last task in the array. So we can do this to get the last task. And then we're going to unlock. So effectively, it's taken a task from the pool. And now we execute that task. But we didn't actually tell it to start. I think someone just knocked on the door. Excuse me. How do I pause? Okay, we're back. Someone delivered a package. Where were we? That's right. We just added the ability to start the thread pool. So we should do that. So if we start the thread pool, it should create a thread, which is going to wait for something to be added to the thread pool. Then we add something to the thread pool, so it should execute it. But it seems like it does not, because we should get task printed out. So we call thread pool start. So it should have created a worker. We should wait, take something off, and execute it. I don't know why that would not have done it. So let's put some well, maybe not there, but let's put some debugging in here. So print line sleeping, awake, executing task. Oh, we don't even get sleeping. So it's like it's not, I mean, index is less than. Yeah, that's probably why. Okay, sleeping, awake, executing task. Then we get task, and now it's sleeping again. That makes sense. But you can see that the program never exits. So to allow it to exit, we also want to be able to stop the thread pool. And the way I'm going to do that is I'm just going to send a signal per worker. So usually up till now, we've only signaled when there was something to process. And now we're signaling when there's nothing to process. So in our worker, what we're going to do, I'm going to move this up here, and then I'm going to say, so first we lock, and then I'm going to say if the task count is 0, if there's nothing to process, we're going to exit. Otherwise, we're going to do what we were doing before. So how do we exit? We want to make sure we unlock always. So maybe I'll put the unlock after the if else actually. Oh no, because it needs to be before we do this. We don't want it to be, we don't want to keep the lock while we're doing the execution, because this might take a while. And if we hold on to the lock while we're doing this, then other threads are not going to be able to pick up new tasks and start them. So before this, we need to exit the loop. Like we could do a return, or I'm just going to make like an alive variable and then just say alive equals false. So it'll loop around and then it just won't it won't execute again. So if we receive a signal and there's nothing to do, then we'll exit. And when we do thread pull stop, it just adds enough signals so that after whatever tasks have already been added to the list are done, all of the workers should exit. But we did not call thread pull stop. We should probably actually call it. There, so now we get exit code 0, so the program exited. It executed the tasks, it slept, then it woke and had nothing to do, so it exited. Cool. That's very nice. And we could do like 3 tasks. Maybe we can get rid of a bunch of this debugging text now. Yeah, so we can run 3 tasks. That's very nice. But a thread pool with a limitation of only having 1 thread is not fantastic. I think it could be better. Like I mentioned before, we only support 1 thread right now. The main reason for that is that we do this. We just have like a little bit of space that we statically allocate, and we use that as the stack for the thread that we create. So if we make multiple threads, they're all going to use the same stack, and they're going to override each other's stacks and cause all sorts of mayhem. So to resolve that, I think we need to make sure we allocate memory for each new memory each time we make a new thread. So we'll definitely get rid of that. And I'm going to move this code. I'm going to try and implement it in our language actually, instead of having it hard-coded in assembly. So we'll take this definition away. I won't take this away yet because it would be handy to maybe use as a reference while we're doing this. So one thing we need to do is be able to allocate memory, which in Linux is the mmap procedure, or mmap syscall. So I do have some grok investigation open here, and here's an example of doing it. So the system call is number 9. And what we need to pass in is, we can optionally pass in an address that we want to use. I don't know how that kind of thing works. But what I'm doing so far is I'm basically just adding support for whatever parameters there are, even if I don't really know how to use them. So there's an address, then there's the length, so how much memory do you want to allocate? And then there's prot and flags, which is 2 kind of like, they're both kind of like flags. So we can read and write. I don't really know this stuff, private anonymous. Then we have a file descriptor, which we're going to set to -1, and an offset, which we'll set to 0. And like, yeah, a lot of this stuff I don't really know how to use it, so we're just going to use the example. So it's a length i64 prot, i64 flags, i64 file descriptor, i64, and what was the other one? Offset, i64. And we're allocating memory, so we need to return a pointer to that memory we just allocated. So I'm going to go like that and then return, because this will be an i64, so we'll just do untyped so that we can convert it to this type. Okay, so go address, length, prot, flags, file descriptor, offset. That's basically it. That's some mmap call. And now I guess I'll put it here maybe. No, start thread is a procedure, and the first argument, func, is also a procedure which takes an argument which is an I64, and the second argument is the argument itself. So when we start a thread, we want to execute this with this argument. Okay. So the first thing we need to do is allocate some memory. So stack equals mmap. We're going to give it. We're not going to provide an address because I don't know how. I don't really want to. We're going to allocate 4 kilobytes, and so we need. We need these variables, and from the example, the file descriptor was -1 and the offset was 0. So the prot is an I64, which is OX3. We don't actually support hex in our language yet, so we're going to add support for that because I'm kind of tired of like always converting to decimal. So this one's OX22, I think. OX22, yeah. Like so. So that should give us our stack. So maybe we'll just make sure that that works. So we need to support hex. That's in our tokenizer. This looks like the right place. This is where we do our numbers, is it? Yeah. I think I'm just going to create a whole new case because I think it'd be a bit difficult to add it into the existing one. They're a bit different. So if we find OX, then let's consume the OX, and we don't need this period business. And we're going to allow 0 to 9, or A to F is valid for a hexadecimal. Also capital A to capital F is valid. So I think that's basically a hexadecimal number. It should allow it. Incompatible types, line 27. I think that's because we're passing in a boundless I8 as this parameter, but syscall expects all I64s. Start thread inconsistently redefined. Okay, so we will cut this out. We can always just have a look at it like this because it's been defined twice. Okay, exit code 0. So at least no errors so far. Now this is where things get tricky because we need to prepare this stack. Maybe before I do that, it might be a bit easier to explain if we do the clone call first. So PID equals syscall, I think it's 56, with some clone flags and stack I64. Now here I'm doing syscall directly instead of wrapping it. Like most of these syscalls, you know, I wrap it, so I've got like a write, which wraps syscall 1. I've got mmap, which wraps syscall 9, exit wraps syscall 60, etc., etc. But here I'm not doing that because it's going to simplify this crazy stack stuff that I'm about to do if we don't have yet another call. Because this is going to evaluate just to like some syscall assembly, so it's not actually going to do a call. which would require more stack preparation if using our calling convention. And when we do the clone, it returns a PID. And if the PID it returns, so what happens is, this is where it gets a bit crazy. So after the syscall, now the thread that called start thread will continue down here with the PID of the new thread. And the new thread will also continue from this point with a PID of 0. So by saying PID equals 0, that means we know we're in the new thread. So the new thread, what we want to do is call the function that was passed in and then exit. And on the existing thread, we want to return the PID, why not? And then just continue doing whatever we were doing before. So this is kind of like the basics of it. Let's do stack i64 is an i64 version of stack. And clone flags is this, which represents all of these flags. Okay, so first we allocate some memory. Then we do a syscall with that memory. The thing is, though, that stacks go backwards. So you need to be at the end of the stack is where you need to start. So that's why I've taken this address and I've converted it to an i64. So now we have an i64, which is the address of our stack. So now we go to the end of the stack, because that's what this is, the syscall is expecting, the clone. But we need to go back the size of two 8-byte values, and that's because that's these two arguments. We need to have space for these arguments. They need to be in the stack of the new thread because it needs to use them, right? It needs to access them. So we need to add it into the stack. So we're going to move our pointer to there. And also the way our calling convention works is that 0, or like, yeah, our stack pointer when we enter the procedure should be at that point. So we'll say account for params. And then what I'm going to do is say stack params. I'd say that's a pointer to an array of two i64s, which is a conversion of this. So that pointer, now we're saying that this position in the stack is pointing to an array of two i64s. And we're going to put the parameters in there. I think I've got these down the right way because we're like moving backwards kind of. Yeah, we're moving backwards in the stack. This is the last one, so it should appear at the end. Yeah, it's a bit confusing, but I think this is around the right way. So now I think we have our parameters in the stack like we need. If we go back to the way that our stacks work here, so we've just added these two in. Now we need to account for the instruction pointer and any variables that are in the procedure. So we can account for instruction pointer, which is 8. The reason I'm putting brackets here is because our precedence is no good. We need to fix that up as well. and it might evaluate this before this, which would be bad. So stack, yes, we've accounted for that. Now we need to account for the local variables. Declared before clone. So up to the point where the child thread is going to start, we need to make sure that all the space taken up by these variables is accounted for. So how many variables do we have? 1, 2, 3, 4, 5, 6, 7. And I believe they're all 64-bit. That one is, this one is, that one and that one are, and that one and that one and that. Yeah, they're all 64-bit. And how many did I say? 7. 1, 2, 3, 4, 5, 6, 7. So I'm going to say 7 times 8. So now this stack pointer should be pointing at the correct location such that all the offsets in the assembly are correct. Let's see what happens. Yeah, I would have been surprised if that worked. So let's comment out, whoops, like all this and see whether that works. So that doesn't even work. So let's go like up to here maybe. Okay, that does work. What about here? Okay, so that does not work. Let's have a look. So start thread, the last statement in start thread is dereferencing the last thing that was declared. This is the last thing declared, so dereferencing this makes sense, and then indexing into it at index 1, doing some bounds checking, getting the thing that we want to copy into it, and yeah, because we're at index 1, we're going +8. It all looks right to me. I guess the thing I'm a little bit worried about is whether this is actually a valid address. So let's have a look at that. We can print that out using this kind of code. If we get the stack, and actually something I think this I to A is not actually very good. Like it doesn't really handle negative numbers. So if value is less than 0, I kind of want to add the negative sign. So I need to figure out what number that is. And then negate. So then value becomes positive, and then all this code down here should still work. And I also want to handle 0, because that was a bug that I struggled with for ages. So if the value is 0, then I just want to say, look, put a 0, and that's it. And then it won't go into this loop, but we'll actually at least have a 0. So what is the negative sign? If we go to the ASCII table, whoa, let's not zoom in quite so much. Here we go. Minus is 45. Let's close that so we can just put 45 here. Let's run that. Oh. Oh, well, we do still have that, but why is it not printing out? Huh, it's not printing out anything. Okay, so now this seems to be buggy. This is a 64-bit value. I2A. I do think there might be issues actually with my, like I want it to be that the ordering of the procedures does not matter, but I think there might be issues with that. So let me just temporarily chuck it up above. Yeah, that's what it was. Okay, so we get like a nice big number. That I think that's a valid I think that's a valid stack address. So let's maybe go like that. That's right, it was there that we had the issue, wasn't it? This untyped func. One thing that I did want to add, I don't think it's the case here, but when we're type checking an identifier, first we check if it's a struct member, then we check if it exists. And if it doesn't exist, we need, I think what we're missing is undeclared. So if we don't allow undefined variables, then we should say is not defined so it's no dot value like so. And this is basically, this is for right hand side expressions. On the right hand side, so I think this needs to go here. On the right hand side, we don't allow undefined. On the left hand side, we do allow undefined because they will just define it. So on the off chance that this then says, hey, I don't know what func is, but it does not say that. So why is that? If I just say like 1, it still doesn't like it. I do feel like this is somehow invalid memory. Like, why else would it complain about this? Because the assembly looks, start thread, the assembly looks fine. It's just grabbing the top of the stack, doing some bounds checking, and then moving 8 bytes into it. Like, it looks fine to me. So I think it's, I would think that it's like to do with the, oh, what? How is that valid without the equals? Wow. Okay. Okay, so let's try the whole thing on the off chance that it works, and of course it does not. Let's try that. So that's happy. Maybe we can take that out. Okay, I had a feeling that might be the one that was not happy. I might move this I2A stuff back where it came from. Where did it come from? Is it just here? Yeah. So it doesn't like this, which leads me to believe that maybe my offsetting is wrong. You know, I calculated my offsets. So here we've accounted for the parameters. Here the instruction pointer. So that's 2 times 8, they're both 8-bit. That should be, 8 bytes. That should be fine. The instruction pointer definitely is 8. 7 times 8, is that correct? 1, 2, 3, 4, 5, 6, 7. That should be correct. That's happy. So why is it not happy about that? Did I get those around the wrong way? I don't think so. Let's try the other way around. Oh, need to go like that. Yeah, I think that's right. Put that back up there and let's print out some other stuff. So maybe we can print out the arg. But it's a pointer, so it's not going to be that helpful, actually. I don't know what we can print out. Well, I guess if we print out stack i64 here, and then we also print it out in here. No, but we don't say we don't actually really copy it into the child, so that's not going to do anything. I feel like this must be wrong. I don't know what else it could be that's wrong. So we add 4096 because that takes us to the end. Then we backtrack 16. We put our parameters there. We're pretty sure we put them in the correct order. We account for the instruction pointer. Then we account for all the local variables. Sorry, the video is getting a bit long, but I feel like we're like this close. We just need to solve this procedure. We don't have anything hanging on here that's conflicting, do we? I don't think so. From the old implementation. So that is failing. If I make that work, but then I clear out the worker, so it doesn't actually do anything. Like, could it be an issue within the worker? Okay, so something is going bad in here. So it is calling, it seems like it's calling it okay, I think. So I can do that, that's fine. I can enter the loop. That seems fine. No errors there. What about if I take that out? That seems fine. If I just never do that. Oh, okay, of course, task is not defined, that makes sense. So that seems happy. So what if we just do that? We just decrement the, okay. Wow, we're really narrowing it down. Is it this line? No, this line's not happy. What? What? I just comment everything out and then uncomment it. And now it works. Okay. Don't ask me why. But that seems to work. And now the last thing, fingers crossed, is I'm going to make 3 workers. Okay. So now we get this kind of funkiness where like the new lines are not in the right places. But that's totally fine. The reason for that is because when we do print line, we're actually calling write twice. So probably we do one write and then it switches to another thread. Like we do a one write of this, then we switch to another thread and we do this. And then both of those threads do their new lines and then another thread does this. You know, it's kind of intertwined. So ideally this would be one call to write for print line and then we would not get this weird mashup of stuff. But okay. Yeah, sorry it was a bit long, but I think it's pretty sweet, right? We've got a thread pool with multiple workers. We can start it, we can create some tasks, we can add them to the thread pool, they all get executed, and then we can stop the thread pool. We have multi-threading. Much nicer multi-threading. Okay, so the next step is I want to make like a convenience. We're just going to do a basic first one, but I want like a convenience feature that will allow us to spread the processing of an array across multiple threads. Yeah, so we'll have a go at that. I think once that's working, we're going to get stuck back into tests because we really need to test the hell out of this thing. Cool, I'm happy. Thanks for sticking around for a long video, but I think this was pretty sweet that we got a thread pool working. That's a pretty cool feature. But yeah, thanks for stopping by. Have a good one. Ciao for now.